All right. Hi, everybody. Can I ask you guys to stop talking, please? Thank you. Today, to start, you got a whole bunch of homework dumped on you last time, right? Do you have some questions that you want to ask about things that you've started or seen or weren't sure what to do with? Or I'm happy to do any of that kind of stuff. My new friend, Megan Tompkins, will start with you. 22. Sure. So this says two toy racetracks form concentric circles. Let's pause there. Do we know what concentric circles means? So that's two circles who share the same center. So like, give me another one here. I'll do something like that. So when we say concentric circles, we mean something that kind of looks like this. Each racetrack is divided into 15 identical sections. So we'll say that one of those identical sections maybe looks like this. I'm not going to draw all 15 of them because I'm pretty sure I would screw it up and they would not look anything close to identical. If the inside car travels 1.2 centimeters less than the outer car on each piece of track, how much bigger is the radius of the outside track compared to the inside track? And then it says, gives you some idea of how to do this. Okay. So I'm going to call this radius 1. I'm going to call this radius 2. Okay with that, Megan? And I'm going to call this arc length 2, and then this one arc length 1. Okay with that. So I know that, say, S1 is going to equal to R1 times theta, and S2 is going to equal R2 times theta. Okay with that. Since both of them have the same central angle, so our central angle is going to be 360 divided by 15 because we divided it into 15 separate sections. Or because the formula up here we wrote was the radians one, I could think about it as 2 pi over 15, or 2 pi over 15. That's the way that I'm going to choose to do it. Alternatively, you could have used the degree formulas. Megan, that would have been fine also, and done everything in degrees. You're still cool? Okay. And it says then that the inside car travels 1.2 centimeters less than the outside car. So I can say that S1 is equal to S2 minus 1.2. And we're asking how much bigger is the one radius than the other. Okay. So we have that. So I can say that S2 then, my 2 is equal to R1 times theta. And if I add the 1.2 over, I have this. And then if I take this equation and substitute it, because they're both equal to S2, I can do that. I can say R2 theta is equal to R1 theta plus 1.2. Okay. Still so far so good? And I realize that theta has a number associated with it, but I just didn't want to have to keep writing that number down over and over and over again until I was ready to really just do it one time for the final. Is that okay? Okay. So it's asking how much times bigger is the one compared to the other, right? It says how much bigger is the radius of the outside track compared to the inside track. So if I do and subtract r1 theta from both sides, I have this, and I can factor the theta out, and then divide both sides by the theta. The difference in length between the outside and the inside is going to be r2 minus r1, right? So now I just need to solve this. So now I'm going to go ahead and plug in the 2 pi over 15. So when I make a reciprocal and multiply, I have this, and then it's calculator time for me. So this should be 28 point, or I should say about 28.3 centimeters longer. Or that difference is about 28.3 centimeters. Is that right? I guess I could look up the answer, huh? Feels like that's what I'm supposed to do. Hi, Miss Williams.
Hello, Mr. Fuller.
How are you?
One more exciting item.
Oh, just what I need, more things to grade.
I know, we need more excitement.
Have a good day.
You too.
Mm-hmm. Okay. One hot second while I look this up real quick, because I don't want to stop if I have the wrong answer. You know what I mean, guys? It's not a lot of good to you guys. I should have these printed out. I don't know why I didn't, but, you know, we all make mistakes. That was mine. Next time I holler at you for being prepared for class, you can be like, well, you didn't have the answers all printed out last time. I'll be like, you know what? You're right. I can't be mad. All right, let's see. That's interesting. Separate sections. The inner one is 1.2 less than the outer. On each piece of track, no, that's fine. Oh! No. Okay, so the smaller one is 1.2 less than the big one. So I did that, and then I added that over, and then I rearranged those. And the difference between the big one to the little one should be that. And divided by 15 is that number. Which is that. Oh, I know what I'm looking at. Well, this is right. The answer in the book just has it the wrong decimal place, or the answer that in mine has it in the wrong decimal place, I believe, is the issue. But the approach is fine that we did there. Let me make a little note for myself to go back and make sure I update that. So sorry for the delay there, Megan, but I want to make sure before we stop that things were correct. And now my computer wants to be a sluggo. Who's next? Oh, I don't. No, you got to tell me. Bridget, what's your last name, Bridget? Galbraith. And I've asked you this before, and I should be better. Number 20. Sure, this one is, I think, so 20 says find the perimeter of a sector cut from a circle with radius 8 by an angle measuring 1.21 radians. Do we know what we mean by a sector? Yeah, so a sector is like a slice of pizza. So we're just looking for this arc length. So I'm just going to use S is equal to R theta. So the radius we're told in this case is 8 inches. And the angle is 121 in radians. So I'm going to use the Radiance formula like I wrote down. So I think all I have to do is legit do 8 times 121. Looking at the wrong solutions or something here. No, there should be the right file. How in the heck did they get? So we have that. Bridget, I was quite confident that's done correctly. It's not at all the answer that I have written down here, so I'm just looking this up to make sure I haven't done something like colossally stupid when I've done my work here. Yeah, so since it's the measure of the angle is given in radians, you don't need that one. You can just set them right there next to the podium, would be perfectly fine. Thank you, my good man. So that should be the right answer. Why is it not at all what I have written down? But yes. So, oh, of course. Yes. So the perimeter is this plus R plus R. Boy, that you guys are just geniuses. I don't know why you're asking me the questions. I should be asking you the questions. Thank you. Next time I'm sitting there being stupid, you can tell me about myself earlier, and we don't have to waste as much time watching me hum and haw about the whole thing. Excellent. Thank you. That's spectacular. Bridget, you happy with that? You're welcome. Okay, Dan. 24. Okay. Circular saw has a diameter of 8.25 inches, and there's 12 teeth per inch on the cutting blade. If the saw spins at 3,500 RPM, how many cutting teeth cross the surface each second? So I'm just going to treat this as a unit conversion problem, I think is probably the easiest way to do this. So I'm going to have 3,500 revolutions per 1 minute. And the answer we want is teeth per second is what it's asking for. So I'll start by just converting minutes into seconds. So I know there's 60 seconds in 1 minute. So now I'm in revolutions per second. So I have the per second part done. You cool there? Now I'm going to start translating revolutions into teeth. Version that converts or that relates teeth and linear distance. So what I want is a ratio that converts or that relates linear distance to revolutions. I know that 1 revolution is equal to 1 circumference. So in this case, that's pi times 8.25. Remember that circumference is pi times the diameter, or 2 pi r. Either one is the same thing. So I have 1 revolution is 8.25 pi inches. 1 inch contains 12 teeths. So if I look, I canceled the revolutions, I canceled the inches, and I'm left now in teeth per second. So I should just multiply that stuff out, and I should be good. Do you guys buy that? So I get 18,140.7, and probably would want to round that to the nearest tooth. Oh no, it's teeth per second, so that's probably fine. I can have if it's a rate, that's not unreasonable. Dan, are you happy there?
Yeah.
Yeah, no problem, man. I did that one better than the first one. Megan just started with the hardest one and got me all flustered. All right. Who's next? Isabella. 39. You were busy last night. Well, maybe not last night. It could have been 2 nights ago, right? We don't know. I shouldn't presume. So here's my right triangle. And we're told that A, B, C, angle A is 38 degrees. Side B is 10. And we want to solve for side C. So I'm going to use angle A. Relative to angle A, side B is the adjacent side. And side C is the hypotenuse. So the trig function I'm going to want to use is cosine, because cosine is adjacent over hypotenuse. I'm then going to set up a proportion and do my cross multiplying. So I have C times cosine 38 is equal to, and then if I divide both sides by cosine 38, I have C is 10 divided by cosine 38. And then I just have to make sure before I type this into my calculator that I'm in degree mode. If you feel like you did the problem right and you're not getting the right answer, that's a good place to check. Oh, it says round to the 100th. 1269 should be my result. Does that feel okay there? Cool. Anybody else? Yes. Julia. DeMeglio or something. Was I close? I was even right? I get bonus extra credit for last names. 23, sure. Now that I've embarrassed you enough, right? So 23 is another unit conversion problem. So we're told that Danny is riding a bike that has 22-inch diameter wheels, and he can ride it at 14 miles per hour. And we're asked how many revolutions per minute are the tires making, round our answer to the 1,000. Okay, so I'm going to start with the rate that we're given. And I'm going to try to end up in this revolutions per minute. Okay? So first off the bat, I'll do the time conversion. So I know 1 hour is 60 minutes. So now we're in miles per minute. And then I need to convert between, or find a way to convert miles into revolutions. Well, just like we said earlier, we note that 1 revolution is equal to 1 circumference. So in this case, that's pi times the diameter of 22. But that's in inches. So first, before I can do that, I got to convert miles into inches. But then I'll use that ratio that we just came up with. So I know 1 mile is 5,280 feet. And 1 foot is 12 inches. And then 22 pi inches is 1 revolution. And now I just need to grind out that calculation because we've gone from miles to inches, or I'm sorry, miles to feet, from feet to inches, and we're left in revolutions per minute. Does that feel okay? And the place where the most likely place for a mistake here would be when we divide by 22 pi. If you did a division bar on your calculator, you need to make sure you put a parenthesis around the 22 pi, because if you just type divide 22 pi, it's going to divide by 22. Take that answer and then multiply it by pi. The other alternative, if way that you could have typed this into your calculator that I think would be a nice effective way to get the correct answer without having to worry about that, is if we use this fractions and I pick that first option, the n over d. That'll give me the little fraction here, and I can just type it in straight across like 14. I won't bother to type the times 1, but times 5,280 and then times 12. In the bottom, again, I'm not going to bother with the ones, but then I'll have 60 times 22 pi. 22. And if I do that, then I don't have to worry about like accidentally goofing up the division by 22. And that's the way I would type it into my calculator. It makes life a little bit easier when you don't have to worry about the parentheses and stuff. Because it's just what it looks like on your sheet of paper now, which is always nice, right? Because the calculator is kind of dumb about stuff like that. It does what you say, not what you mean. Yes. What's your name though first? Leah. Greif. Yes. Not grief. Of course. 44, it says, find values of 2 different angles coterminal with the given angle. One of your answers must be positive and the other one must be negative. Okay? So our angle that we're given here, I'm going to just call theta, which is, we're told, 2 pi over 7. So we know that we can find an angle coterminal by adding 1 full rotation. So in degree speak, 1 full rotation would mean adding or subtracting 360 degrees. In radian speak, we're adding or subtracting 2 pi. Okay with that? So one answer, since I already have a positive angle, I know if I add 2 pi to that, I'm certainly going to get another positive answer, right? To add those, we're going to make a common denominator with the 7. So it's going to give me 16 pi over 7 as one possible answer. But you could keep adding and still be getting answers that are acceptable for your positive angle. Are you good with that, Leah? Okay. For our negative angle, I'm going to just subtract 2 pi, and I'm going to do that as much as I have to get a negative answer. Now, it's only going to take one subtraction to do that in this case, but if I didn't get a negative answer, I would just keep subtracting until I get a negative one. Are you okay with that?
Yeah.
Okay. And the only reason I'm looking for a negative here is because the directions ask for one. So these are the quickest 2 answers that you get, although there's an infinite supply of correct answers, right? If you subtracted another 2 pi, you'd still have another negative answer that's coterminal. And you keep doing that and doing that and doing that and always get a correct answer for this. It's just, why would you keep going, right?
So you're trying to find if like 2 angles are coterminal, you're trying to find if they're like 1 or 2.
Well, it could be more than 1 rotation apart. What I would do if I were to do that is I would try to, if you wanted to say is like 1080 coterminal to, I don't know, what I would do is I would take them and put them both into angles between 0 and 360 and see if they're the same angle. So I'm just going to subtract 360 a bunch of times. So like 1080 minus 360 is 720. That's not between 0 and 360. Or I can just kind of pause here and just do all my subtractions from 360 from the other number and see if I run into 1080 along the way. Then taking them both down to a number between 0 and 360. I'm just going to keep subtracting 360, and you'll see that if I do that, I do run into 1080. So you could say right there that that's enough to say that those 2 angles are coterminal.
Okay, so I think like degrees you do like between 0 and 360.
Well, you don't even have to necessarily get them both between 0 and 360, although that will work.
Yeah.
You can just keep subtracting or adding 360 until you make one of them the same as the other.
But if it's in like radians, you try to get it with 2 pi.
You would use 2 pi's.
Okay.
Yep, exactly right. Dan.
31.
31? Okay. Exactly. Yes, so it's the exact value of sine without using your calculator. So pi over 6 should then be either 30, 60, or 45, or else we can't really do this problem, right? So let's convert it into degrees to see which one it is. So to convert radians to degrees, we multiply by 180 over pi, which gives us 30 degrees. So once I know that, I know I'm just going to be using my 30, 60, 90 triangle. So sine of pi over 6 should be opposite over hypotenuse, or 1/2. If pi over 6 wasn't one of these 3, we don't have any, right now anyways, an exact way of calculating that. Everybody cool with that idea? Bueno. Ben?
I just don't like understand how something's coterminal when it's
So let's say that we have one angle that is 2. (41π/4). And let's say we have another angle that is -23. Okay with that? Yeah, -23π/4. So what I can do is I can either keep adding 2π to this one and see if I can get to here. I could subtract 2π from this one to see if I get to here, or I could do both, add and subtract from each of them and see if I meet at some value in the middle. But I'm just trying to turn one into the other.
Okay, so like if you're like the left one to the right,
Okay?
so you just keep on subtracting 1π/4.
8π/4. Yep. So if I do that, I have then 33π/4. And then it would go to 25π/4. And then what? 17. Right? They should keep staying odd because we're doing them even from an odd. 9π/4. And then that's 1π/4. And then I have -7π/4. 15π/4, and then -23π/4. So they're coterminal. Does that, everybody feel okay with that? Leah, that's the same kind of question that you asked. We just did it in radians instead of degrees.
Yeah.
So we just picked one and tried to turn it into the other. And we did that either by adding or subtracting 2π's.
So you did 8π.
Well, 8π/4 is the same as 2π, right? I just turned it into a common denominator so I could do the subtractions. Does that feel okay? Okay. Who's next? Yes.
Did you ever like me?
Yes, can you tell me your name first, please? Tess. But it's not the way I want to pronounce it, because we tried this before.
No, Kenza.
Chensoni, yeah. I remembered it's not Sessoni, at least. It's like she'd already told me that's not the way, and now I forgot the number. 19. Okay. Says 2 concentric circles are cut by the same angle. Okay. We mentioned what concentric means, so we'll just pop out a drawing here. Okay. Something like that. Cut by the same angle. So we'll do that. So there's my angle. The radius of the smaller circle, I'll call that R1, is 4.3 inches. I guess I'm guessing that should be less than the cut arc measures. Oh, it just is. Sorry, 4.3. The cut arc measures 5.2. Okay, so that's the little stuff. The radius of the larger circle, I'll call that R2, is 5.2. What is the radius of the cut arc? Okay, there. So here, and I'm going to do this in radians, although it doesn't matter if you use degrees. So I'm going to figure out this angle theta because it's the same angle theta for both situations, right? Because the central angle here is the same for each of them. So I know theta is S1 over R1. So if I come over here, I know that S2 is R2 times theta, or really R2 times, and I know R2, that's 5.2. I know S1, that's 5.2. And I know R1, that's 5 or 4.3. And there, I just have to type that into my calculator. Does that feel okay there?
Yeah.
Yeah, no problem. So just a about jigging, them around in the right fashion. The key observation, though, is that theta was the same in both situations. So I can use the smaller one to solve for theta to using the bigger one. Okay, you guys feel good? Or better anyways about the homeworks? There were some tricky ones in there. Some of those story problems were kind of buggers. I think probably the hardest questions in here were some of those story problems. Today, we're going to finish up where we left off. Where did we leave off? Do you guys remember? Let me look real quick. Okay, so we just did coterminal for angles of rotation. So we finished 2, 3, right? Yes, okay. Okay. All right. So remember at the beginning of the semester we talked about one of the first things that we're going to want to do in this course is to generalize our definitions of sine, cosine, and tangent so we can apply them to angle measures other than just those inside of an acute triangle. We want to break free of that definition and extend the definitions for sine, cosine, and tangent so we can operate outside of right triangles. Everybody's okay with that? We kind of remember me mentioning this? Okay. So yesterday, what we did is we talked about, okay, well, I can take an angle and embed that angle inside of the xy axis, and now I can define an angle of any size, right? Could be negative, could be positive, could be as big as you want, can be as small as you want. I now have a way to define an angle for any measure you can name. Everybody's okay with that? What I'm going to do now is I'm going to adapt our definitions for sine, cosine, and tangent to meet this kind of angle definition. So to do that, what I'm going to do is I'm just going to pick some point on the terminal side of my angle. I'm going to call that point P, and I'm going to give it the coordinates x, y. So P is any point on the terminal side of that angle. Everybody's okay there? Now I'm going to make a right triangle by drawing an altitude, or I'm going to line back the x-axis. Everybody's okay there? So I have this new right triangle. What is this length? What is that leg length there? Gotta be. Megan? Yes! Why is it gotta be y? Well, we graph a point, we go x over and then y up, right? So to get to the coordinate xy, we went x over and then y up. So that side length has to be y. Everybody agree with that? Okay. What is this side length got to be then? X, right? By the same token. Is everybody okay there? Okay. And now what's the hypotenuse got to be then? The square root of x. So we're going to call, because that's a lot of symbols going on there. Is everybody okay with that? Okay. So now I've found a way to translate our angle measure, that's an angle of rotation, it's embedded in the xy axis. I found a way to translate that into a right triangle. So if I use my old definition for sine, cosine, tangent, secant, or cosecant, secant, cotangent, I can say that sine is opposite, which in this case is y, over hypotenuse, in this case is r. Cosine, which is adjacent over hypotenuse, so x over r. Tangent, which is opposite over adjacent, so y over x. Cosecant, which is hypotenuse over opposite, so r over y. Secant, which is hypotenuse over adjacent, so r over x. Cotangent, which is adjacent over opposite, so x over y. Notice that these new definitions of sine, cosine, and tangent no longer depend on sides of a right triangle. They depend on the coordinates of our point and the distance from our point to the origin. Is everybody okay with that? This is a good step in the right direction, right? So we've gone and taken sine, cosine, and tangent being linked to a right triangle, and we used that definition to extend out. So now that sine, cosine, and tangent are dependent on some point on the terminal side of our angle of rotation. So now if we wanted to do like sine of 240, we can do that in a way that we made no sense before when we were stuck with right triangles only, because you can't have a triangle with a 240-degree angle in it. So for example, let's say that 4 lies on the terminal side of the angle theta, or the 6 trig ratios for theta. Well, to do this, we know x and we know y. So r is just going to be negative 3 squared is 9, plus 4 squared is, which is 16, comes out to be 25, and the square root of 25 is 5. So I can just use my definitions up here, right? Because I know x, y, and r now. So sine 4 over 5. Cosine of theta is negative 3 over 5. Is 4 or negative 4 over 3. Cosecant theta is 5 over 4. Secant theta, 5 over 3. And cotangent theta is negative 3 over 4. Everybody okay there? Yes. Of course. So the next thing we're going to do is try to find the exact value of sine of 150 degrees. Okay, well, we'll start by drawing a 150 degree angle. So our initial side is over here on the positive x-axis. We go 90 and terminal side. So that's 60 degrees, which means that this angle here has to be 30 degrees, right? Is everybody okay there? Everybody's clear as to why those were 60 and 30 degrees respectively? Okay. Now I'm just going to pick some point. There's my point P that's on the terminal side. And I'll draw my right triangle back to the x-axis. When I do this, I'm always drawing back to the x-axis. And what kind of triangle have I just drawn here? It's a 30, 60, 90 triangle, right? So I know this other angle is 60 degrees. So this side is x square root 3, this side is x, and this side is 2x. So sine of 150 is going to be opposite over hypotenuse, or just 1/2. Now I've done something that's not quite right when I drew in these coordinates. Remember that these side lengths, I should say. Remember, these side lengths to my right triangle don't represent side lengths here. They have to represent the coordinates of our point P, right? So notice where we're at. We're in the second quadrant. So this value should really be negative, right? This value should still be positive. So this didn't affect the answer for sine of 150. But if we instead wanted cosine of 150, here we should have negative x root 3 over 2x, or negative square root of 3 over 2. Is everybody okay there? Dan?
So, from my point of view,
Mhm.
sine, it's like opposite over hypotenuse, so wouldn't it be like x squared is 2x, not x over 2?
Oh, sure. Thank you. Oh, wait a minute. For sine?
Yeah.
Okay, I'm sorry. The truck or the bus or whatever was going by where you were saying something. Can you repeat what you just asked?
Like, where are you referencing?
Okay.
For sine of 150 from?
So I can think about it two ways. I can think about it as y over r. So y over r. Okay with that? So the y coordinate of point P is definitely x, and the distance from the origin to the point P is 2x. Are you good with that? Alternatively, we can think about just using our right triangle definitions, using that 30-degree angle there. So it would be opposite over hypotenuse. Are you okay with that?
I mean, I'm just like confused on why using it from like a 30 degree. It's like
Because this was the way we translated between an angle of rotation back to a right triangle. What we did is we picked a point P on that angle of rotation, and then we drew down to the x-axis and made a right triangle. And that's going to give us equivalent values for sine. Excuse me, guys! Stop talking. It's going to give you an equivalent value of sine, cosine, and tangent. So that's the way that we kind of translate it back and forth between an angle of rotation and an angle inside of a right triangle. Is that okay? Okay. All right. So we can do one thing a little bit better than this, though, even. So we're not completely there, although what we've given is perfectly accurate, and will do perfectly, but we can make a small improvement here. The improvement is selecting point P. That's that point on the terminal side of our angle. We're going to do this so that the distance from P to the origin always 1. So what does that mean about where point P is at? Or what kind of shape point P will make? The distance is always 1. No matter where we place point P, it's going to be on a circle with radius 1. Does that make sense to everybody? If the distance is always 1, anywhere you pick on that angle of rotation, wherever that might lie, that point P is going to be some point on a circle. So we know that P is always a point on a circle of radius 1 centered at the origin. A circle with radius 1 is often referred to as a unit circle. Since its radius is 1, it's 1 unit. We call that a unit circle. So if we do that, then our definition of theta, let's redraw the picture before we do that. Actually, let's use this. That's fine. That's pretty close, right? So there's that unit circle. I tried to get the origin so that it was right at the center of it, but I can only eyeball it with one note. Everybody's okay with the picture that we've drawn here? So before, we had that, say, sine was y over r. But if r is always going to equal 1 now, sine just turns into y. Similarly, cosine was x over r. But if r is just equal to 1, cosine is just equal to x. tangent was y over x. If r equals 1, that doesn't change anything. We're still y over x. Cosecant, but if r is always going to be 1, we have that cosecant is 1 over y. And secant is x over r. But if r is always going to equal 1, secant is 1 over x. And cotangent was x over y. 1, that doesn't change anything for us. Cotangent just stays x over y. Okay with that. Okay. So, where's that? What we're going to do now, all right. It's going so slow. Trying to find a file that I want. That wasn't where I thought it would be. And now this silly thing takes forever to run a search now because they want to connect everything to the web. All right, whatever, go away. I'll find it myself. You ever get mad at the computer? Happen. God bless you. You're welcome. Oh my goodness. All right, I can't do this anymore. I'll find it later. It's fine. We can do it without it. That's fine. Okay. So what we'll do, or what we can do now, is we can embed so we have our unit circle. And inside of this, we have our xy axis. So what point is this going to be? 1, 0, because we know the radius of this circle is 1. Everybody okay there? This point up here is 0, 1. This point over here is negative 1, 0. And this point down here is 0, negative 1. Okay? So in degrees, this is the 0 degree angle. This is a 90 degree angle. This is a 180 degree angle. This is a 270 degree angle, right? In radians, this is 0 radians. This is pi over 2. This is pi. And this is 3 pi over 2. Is everybody okay with that idea? Yes, Delaney.
How flipped is it just because you have it doesn't become pi,
So that we can, the conversion between degrees to radians is multiplying by pi over 180. So that's where the pi's are coming from. Is that conversion factor? Is that okay? Okay. Now what we're going to do is we're going to draw in all the angles that we can find the exact value for. Okay? So one of those would be like a 30 degree angle. And we remember we mentioned earlier when we did one of the homework assignments that 30 degrees was the same thing as pi over 6, right? Everybody remember that? So the y-coordinate here, when the radius is 1, is going to be 1/2. We found that earlier, right? Dan asked this question from the homework about finding the exact value for sine. So we know that the y-coordinate and sine are going to be the same thing. Similarly, if I did the x-coordinate the same way, I'd have root 3 over 2. The next one we can find is a 45 degree angle. A 45 degree angle where the radius is 1 is going to have side lengths root 2 over 2. If you do the Pythagorean theorem on that, you'll find that that gives you 1. So there's my x and y coordinates there. And then the last one is the 60 degree angle, which is the same thing as pi over 6. And when we do that, you'll see that it's the same thing as the 30 degree angle, but the measures are, everything is flipped to the different, two leg distances are in the opposite spots, right? Is everybody okay there? So if I draw a 30 degree angle over on this side, where again, when I say 30 degrees, we mean, I really mean 150 degrees, but what I mean as 30 is this spot here between that angle and the x-axis. We'll get the same thing as this 30 degree coordinate, except which one should be negative, the x-coordinate or the y-coordinate? The x-coordinate, because we're on the second quadrant, right? Oh boy. And then we can get our 135 degree angle, or equivalent to a 45 if we're looking respective to the x-axis. And the same thing is going to be true. It's going to be the same as the 45 degree angle over here, but the x-coordinate's going to be negative. And then we can do the same thing here with a 120 degree angle. That way there's a 60 degree angle with respect to the x-axis. And again, oops, the x-coordinate here should be negative. Is everybody okay with that idea? Okay, my next angle that makes 30 degrees back to the x-axis would be like this one here. That's going to be 210 degrees. Or 7 pi over 6. Oops, those aren't the right values here, guys. Surprised you weren't yelling bloody murder at me. Should be 2 pi over 3. That should be 3 pi over 4. And that one should have been 5 pi over 6. My apologies, but don't worry, I caught it before it was too late. So this, again, the angle that I make respective to the x-axis is 30 degrees. So it's going to be the same as these 2 points, or the same as this point, except since we're in the third quadrant, both x and y should be negative. And I can continue doing a similar construction here. 225. And that is 5 pi over 4. And so this would be negative root 2 over 2 and negative root 2 over 2. And then this one would be the equivalent to the 60 degree angle, so that's 240 and 4 pi over 3. And this one is going to be negative 1/2 comma negative 3 over 2. And then if I make my equivalent 30 degree angle as this one here, if I make 30 degrees back to the x-axis, which is the same thing as 330 degrees, or 11 pi over 6. And that is square root 3 over 2, comma negative 1/2. Here again, same as 30 degrees, but this time only the y-coordinate is negative because we're in the fourth quadrant. And then we have 315 and 7 pi over 4. And that would be square root 2 over 2, comma negative square root 2 over 2. And then the last one is 300, or 5 pi over 3 in radians, and that's going to be 1/2 comma negative root 3 over 2. So if I wanted to, say, compute sine of 120, well, sine of 120 is going to be the y-coordinate from this picture. So it's just going to be square root 3 over 2. If I wanted, say, tangent of 5 pi over 4, well, 5 pi over 4 is right here, and tangent is y over x. which is just 1. And then what if I wanted cosecant of 390 degrees? Uh-oh, what's the problem? 390 isn't on my unit circle here, right? Well, what do you notice? 390 is coterminal with 30 degrees, is it not? So if I do 360 and then 30 more, I'm back here. So I'm just going to have 1 over y, which is the same thing as 2. Okay with that? Do we see how to use this unit circle here? Okay. What if I asked you to find the value of sine theta if cosine theta is equal to 5 over 7 and cotangent theta is negative? Well, remember that the quadrant a point lies in, we can predict by looking at the coordinates, the signs of its coordinates. So if both coordinates are positive, we're in the first quadrant. If the x is negative, we're in the second quadrant, et cetera, et cetera, et cetera. We know that cosine is is x over r. R is a radius, it's a length, it's always positive. So we know that cosine, if positive, has to be in one of these two quadrants. Because cosine is x over r. And the only way for that to give me a positive value, if r is always positive, is for x also to be positive. Everybody okay there? Cotangent is x over y, and if cotangent is negative, either x is negative and y is positive, or x is positive and y is negative. So that means cotangent would have to be here, or theta would have to be here or here. Everybody's okay with that idea? So what's the quadrant that's in common? The fourth quadrant. So I can tell this is the location of my triangle. So whatever this side length is has to be negative. I can find the length of that side length doing the Pythagorean theorem. 7 squared equals 5 squared plus b squared. That b is going to come out to be 2 root 6. So now I have everything I need to calculate sine of theta. So that's going to be opposite over hypotenuse. Is everybody okay there? Now you'll notice a couple of things when I've been doing these problems. You'll probably have noticed me going back and forth between like the right triangle definition and the angle of rotation definition and this unit circle definition, moving fluidly back and forth between these so that I can do things quickly. That is an important skill to develop. Okay? Understanding the relationship between these 3 different ways of defining sine, cosine, and tangent so you can do things quickly and easily is really an important skill. And something I'd like you to keep in mind when you try the last of this homework set is thinking about moving fluidly between these definitions. That is the most important skill from this first chapter, is being able to translate back and forth between these different definitions. It makes life so much easier going forward if you're able to do that.
Let's stop everything else as we lift up our hearts to God in prayer. The Father, the Son, and the Holy Spirit. Amen. On this Constitution Day, is there a prayer of thanksgiving that I want to make to God for our country, or a prayer of petition? Lord God, we ask you to continue to bless each of us and all of us. In the name of the Father, and of the Son, and of the
Okay, real quick before you leave, just listen for one quick
You
second.
can dismiss students as you're ready.
So the homework check for Sunday is just going to be the book problems. We'll worry about the worksheet and the test review next week's homework check. So we will be having the Chapter 2 test next week. I'll have something up on Power School with the exact date here by Friday. Okay?